Hello, in this video I'm going to explain the magnetic force on a current carrying wire. Okay, in a previous video I explained that the magnetic force was caused by a charge moving through a magnetic field. That is still the case, and if you think about it, since there's if you have a conductor, and so the conductor is just a wire, there's going to be electrons flowing through the wire, which, based on what we have seen with just a single particle in a magnetic field, there should be a force exerted on that conductor similar to that of an electron. Okay, so I drew some pictures over here. And if there's no electrons moving, obviously, zero current, no force. So F is equal to 0. For this one, which I'll call 1, we have a current going in the positive y direction. I made a little thing right here. If you remember in a previous video, I talked about Benjamin Franklin, and how Benjamin Franklin, he did not understand what an electron was. He called it positive. So we went through a lot of our electronics and creating wire and circuitry and stuff, thinking that an electron was positive. Later we found it to be negative. So what we have is a definition of current, which is the direction of positive motion, or positive charge motion. So for example, since the current is going up towards the positive y direction, the electrons are actually going negative in the negative y direction because it's the direction of positive movement. And since electrons are negative, you have to reverse it. So when you try to do the right-hand rule, and that I explained in a previous section, you put your thumb into the page following the magnetic field. You then have your fingers. Your fingers should be pointing down from the screen because the electrons are going down. Now that's kind of odd because the current's going up. So a lot of teachers create a method of having two right-hand rules, which I just find confusing. I use one right-hand rule and it works all the time. So we have our thumb going into the screen. We have our fingers going down, so our fingers are pointing this direction. Our thumb is right here. And so the force is going this direction. Just like a single electron, only now we have an entire wire of electrons. A lot of teachers also come up with the idea of using your knuckles, and they call it the curly right-hand rule. And you'll have your knuckles or your two fingers and your thumb. I can go through all the different right-hand rules in a separate video if someone asks. If someone doesn't ask, I recommend just using, here's your hand. I'm going to just draw a really bad stick hand. Here's your hand, your fingers, and here's your thumb. Actually, that's not too bad. Here's the magnetic field, sorry. Here's the velocity, or movement. Of particles. And then we have the force. This is the palm, which comes out. Wherever you're pushing, you're going to have that magnetic force. So all you have to remember is current is in the direction of positive charge, and electrons move opposite to, or electrons are negative, so they're moving opposite to where the charge is moving. No, it's kind of confusing. Blame Benjamin Franklin. I actually have a book that just ignores this and just says positive charge or positive current is in that of where the electrons are moving. I forgot what it's called exactly, but I'll dig out the book if someone cares. So in this one, we have charge moving this direction. Again, put your thumb into the page. Now your fingers are pointing up, so the force is pushing this way. Pretty simple. There's a couple of things that I'm just going to go over. The force on a segment of a current carrying wire, or just like a little piece of the wire. So say we have this wire right here. If we just cut this off and say here's a segment, I'm going to call this segment L. The force on that particular segment is equal to this. The force is equal to VD, which is the drift velocity, which we talked about again in a previous video, cross product of the current times NA, which is the area of the wire, the number of electrons, excuse me, in a wire, and the length of the wire. Which, if we do some calculus, which some of you aren't in calculus, you probably won't need to even do this. We have the current, since the current is equal to NQ VDA. I talked about that in a previous video too, and that's very important. Because we have the Q, the VD, the N, and the A. So we have the current times the length of the wire, the directional length of the wire, times the cross. I have never actually come across this in any of my examples, but some of you may use it, and if one of you ask, I guess I could create an example for you, which eventually gives you the integral of ds, which is the notation for, again, a segment of that length. So it's basically just dealing with direction again. Cross product B. So this will be segment, and this is the total length. So to get the total length, we add up all the segments. Makes sense. For those of you who are taking calculus, that should make sense. We have a section of wire. We break it up. This is L. We break it up then into little segments, which we're going to call ds. It just goes across. We add up all those, and we get the same as right here, which is the same as right here. Basically, if you take the current times the magnetic field, you'll get the force. The direction, if it's going at an angle, for example, we have a magnetic field going straight up at 90 degrees to the ground, and we have a wire going like this. That is when you need to use that, because you need the angle right here, or right here. You need that angle to actually solve the problem, which will then get you this cross product, which is sine theta I length times magnetic field. That'll get you the total force on that wire. Not the particular point, though. That you'll need to do the integral and break it up into little segments and everything. And that will be for another video if you actually feel like it. Comment and I'll do it for you or suggest it. Anyways, I hope this has helped you understand how current works on a wire. Thank you for watching, and I may give an example at a future date. Feel free to suggest one on my website and I'll get right to it. Thank you for your time.